So this question refers to the Alabama paradox. The Alabama paradox happens when you increase the number of representatives, and that causes a decrease for one particular district's number of representatives. So, for example, let's say that a previous apportionment said there were 30 representatives, and then District D had 12 of those reps. Well, then they decide, okay, we're going to change it from 30 to 31 representatives. If District D drops down to 11 representatives because of the apportionment method, because not all those methods are perfect. The Jefferson, the Adams apportionment method, those all have issues, right? So you've increased the number of representatives. That should mean, if anything, D should at least get one more representative or stay the same. But instead, it caused D to decrease. So that's an example of the Alabama paradox. So when you're trying to decide whether the Alabama paradox happens, you really just have to, run a voting method twice to see whether that decrease happens. Okay, so a college has 10 professors. There's three categories. There's pure math. So I'm going to use P for pure math, A for applied math, and then S for statistics. Professors are apportioned using Hamilton's apportionment method, according to the number of majors in each field. Remember, the Hamilton method is where you use the decimals, and when you first look at the integers. Like, let's say these professors got 6.2. I'm just making up numbers. We haven't actually done it yet. 2.2, and then 1.1. Okay, so if you look at the integers, 6, 7, 8, there's only 9 seats delegated right now. Okay, then you would look at the decimal values, and we'd have to keep going. This one is a little bit bigger than this one, so we give an extra to group P, and there'd just be 2 here and 1 here. So you look at the non-decimal values to decide. There's 6 representatives for group P, 2 for group A, 1 for group S. And then because this has the highest fraction left over, we give 1 extra vote to group P. Okay, so that's just a quick review of the Hamilton method, but there's a video for that on this YouTube page too. Okay, so we've got a population here. There's 4 pure math majors, 12 applied math majors, and 12 statistics majors. So we've got to go through the Hamilton apportionment method. Okay. So the Hamilton apportionment method, we need a total. The total amount of majors that we have are 4 plus 12 makes 16. 16 plus 12 makes there's 28 total students. And then we have to find the divisor, right? That standard divisor, which is where you take the population and you divide it by the amount that's in your, the amount of different representatives you have. Okay, so our population, there's 28 math majors, and right now, we haven't read on to the rest of the problem. Right now, we just have 10 professors available. Okay, so for, let's see, where did I get the number 10 from? Oh yeah, 10, okay, that's the 10, that's the amount of professors. So the standard divisor is 2.8. So for the pure math department, and just a quick reminder, standard divisor means there should be about 3 math students in a particular major in order to justify 1 professor. So the pure math department has 4 math majors, and if you divide that by the standard divisor, then we've got 1.43 roughly. Should have 1.43 professors. So that obviously poses a problem because you can't have 0.43 of a professor. For the applied mathematics, there's 12 students. If you divide that by your standard divisor of 2.8, you get 4.29. And then the statistics department has 12 majors. Divide that by the standard divisor to find out how many professors. 12 divided by 2.8, 4.29. Oh, I think it was this is a tie, right? Should have been, didn't really need to calculate that. It's the same thing. Okay, so with the Hamilton method, first you look at the integers. There's 1 professor for pure math. There's 4 professors for applied and 4 professors for statistics. That adds up to 9. that means we're missing one of the professors because there's supposed to be 10 in total. So we're going to give it to the one that has the highest fraction. We're going to say there's 2 professors for pure math, there's 4 for applied, and 4 for statistics right now. Okay, so that's the first run through. Now they're changing the scenario. They're saying we're going to hire 1 more professor. So we have to redo this whole thing because now we have a different divisor, and we have got a different divisor. That's basically it. We got a different divisor, so that's going to change all the fractions. Okay. And by the way, I don't think I've clicked any in particular, so just don't jump to that conclusion. There's still 28 students. Okay. Still 28 students. That hasn't changed, but the divisor changed because now we have 11 professors instead of 10. So we got 2.55 roughly for a standard divisor. So for pure math, again, you take the number of math majors that are pure math, divide by the standard divisor, and no surprise there. 4 divided by 2.55, we've got 1.57 professors. For applied math, you got 12 divided by 2.55, so we got 4.71. And then for statistics, it's the same thing. It's 12 divided by 2.55, so that's going to be 4.71 again. Okay, so if we apply Hamilton's method, 1 here, 4 here, 4 here, that means we're supposed to have 1 professor, 4 professors, and then 4 professors. That adds up to 9. Now we said our department got increased to 11 professors, so we have to go by the highest decimal, which are these 2 here. We should have 5 professors here, 5 professors here, and 1 professor for pure math. So this is an example of the Alabama paradox because look, we increased the number of professors, and that increase in professors actually caused the pure math department to drop by 1 professor. Okay, so is this an example of the Alabama paradox? We should say yes. Let's see, yes, because the new professor is not assigned to the field with the fewest majors. Yes is correct. Still thinking about that explanation here. The new professor is not assigned to the field with the fewest majors. That sounds okay on first glance. Let's check out the second option for yes. Yes, because while the total number of professors increases, the number of pure math professors decreases. That's a more complete example of the Alabama paradox. Okay, that's what we were just saying. Before, when we had 10 professors, 2 went to pure math. Now, if we increase it to 11 professors, that suddenly made pure math get decreased. And then we said that's what the Alabama paradox is increasing the number of representatives causes a decrease in one of the categories.